Let's continue our look at protein structures. Let's look at tertiary and quaternary structures. So the tertiary structure, sometimes called the three-dimensional, the 3D structure. This occurs when you have forces. So think of like intermolecular forces and others between the R groups of the amino acids that are in that peptide chain. Okay, so let's go over a few of these forces that can exist here in the tertiary. So we've got the hydrophobic interactions. Remember, hydrophobic means water-fearing. So these are the amino acids that have non-polar R groups that are interacting, and those interactions can lead to this tertiary structure. Then we have hydrophilic interactions, which hydrophilic is the opposite of hydrophobic, so it's water-loving or attracted to water. So we're looking at the R groups that are polar. Now, give me 1 second, and I want to draw you the foundational structure of amino acids. And remember that we have the R group, we have the center carbon, and then on one side we have C double bonded O, O negative, like that. Okay, what we call the carboxylate group. And on the opposite side we have the ammonium group, okay, with a positive charge. Okay, so we have the ammonium group, carboxylate group, we have our hydrogen, and we have our specialized R group on these amino acids. So the hydrophilic interactions are when the amino acids in the chain have polar R groups that will interact. Okay. Hydrophobic is when the R groups here are non-polar interacting. Okay. Salt bridges, what's called salt bridges, they come into play with acid-base R groups. So if you remember back to section 1 of this chapter, the R groups can be classified as non-polar, hydrophobic. They can be considered polar, hydrophilic, and in terms of polarity, they can be further listed or characterized as neutral, as acidic, or basic R groups. Salt bridges, if you think back to acid-base chemistry, acid reacting with the base creates salt and water. So these R groups can interact, and let's say you have an acidic R group and you have a basic R group, and that interacts, creates a salt bridge interaction there between the two amino acids. Okay, that will influence this tertiary structure. Then we have hydrogen bonds. Okay, remember hydrogen bonds are a particular intermolecular force. We see them with a hydrogen that is on a very polar bond, interacting with typically a nitrogen, oxygen, or fluorine on an opposing polar bond. So we can have hydrogen bonds interact or be established between these R groups in the structure. And then the disulfide bonds, okay, disulfides are very specialized. We see these with the R groups that consist of a thiol, okay, a thiol, which the cysteine amino acid has that thiol group. So let me just draw that real quick for you. It's the SH with CH2, and then we have our alpha carbon, our carboxylate group, our hydrogen, and then we have our ammonium group over here. Okay, so that thiol group right there. So when cysteine amino acids are in the chain and they're in close proximity to each other and they can interact, they will form these disulfide bonds, which is one of these forces between R groups that will establish this tertiary three-dimensional shape. Okay, and then the quaternary structure. Okay, your textbook focuses in on hemoglobin, so the oxygen-carrying blood protein. Quaternary structure is where we have a protein, and the structure is two or more polypeptide chains or subunits that are interacting. So we have separate chains, and those chains twist, spiral, fold, interact to create this more complex quaternary structure. And the interaction or the forces that we see in the quaternary structure are the same that we see in the tertiary. So we're going to see hydrophobic, hydrophilic interactions, disulfide, hydrogen bond salt bridges. We'll see those there in the quaternary structure.